Do you hear me? So I'd like to thank the organizers for inviting me, and what I'd like to talk about today is my take on my view on learning in high dimensions, mainly the effect of noise. What do we mean by sparsity? And a little bit about treelets. I'll let my collaborator Anne talk about that more tomorrow. So I'll mainly focus on two issues in this talk. One is different notions of sparsity. Different people mean different things when they talk about sparsity. And the second part of the talk will focus on the way I try to understand the effect of noise, rather than taking limits of n going to infinity or n and p going to infinity. I'm going to keep them fixed and actually look at the noise parameter as a parameter and do small noise expansions. So I'll show how this explains the effect of noise in regression problems, what are the benefits of feature selection, what happens when we do principal component analysis as feature selection, and also how can you use this idea of keeping p and n fixed and just thinking about noise as a small parameter to develop a new rank determination algorithm, which, as far as I know, it's better than other things that are available today. So, well, the general framework of learning problems is, I don't need to introduce it. You have p-dimensional data, and you have a response y. And throughout the talk, n will be the number of samples and p the dimension. And there are supervised tasks and unsupervised tasks. And today, I'll focus on a regression problem where y, the response, is a real number. And, well, there can be essentially three different settings. The classical setting, case 1, n is large, p is small, everybody's happy. Case 2, n is large, p is large. Not exactly sure what we do, but there are many different things that one can try and do. And the case that I'll focus on today is case 3, when you have a small number of samples, a large dimensionality, and essentially you're unhappy because you're going to have to put in additional prior information in order to solve what you want. And as also Emmanuel said before, there are many different applications where this happens: gene expression data. I myself was interested in spectroscopy applications, signal processing, etc. So first of all, you could ask, how difficult is it to learn a general function in p dimensions? And there is a famous paper by Stone from '82 which showed that if you have a smooth function and you measure y m of x plus epsilon and you measure risk as just the L2 norm, then the asymptotic error is n to the minus 4 over 4 plus p. This is the same rate that Richard Samworth had in his k-nearest neighbor talk yesterday, not surprisingly. What this means from our point of view is that if you want this to be small, to be order epsilon, your number of samples needs to be exponentially large in dimension. And obviously, people routinely are able to predict things and learn functions with relatively small number of samples, and the question is then why? So there are at least two options, or possibly more. One is that the functions that we're trying to learn are not really extremely complicated or general. The space of functions that we're trying to pick from is relatively small. Another option, which I'll pursue more in this talk, is that the data itself is not really p-dimensional. It has much smaller structures. So for setting A, we typically apply some regularization. For setting B, we typically perform some dimensional reduction. So for example, so here you have different notions of sparsity that have appeared here throughout the talk. One is sparsity or simplicity of the function that you want to learn. Let's say you just decide that your function is a linear function, or maybe that it depends only on a small class of functions. You could even restrict even more. You say not only is it linear, it depends on only very few variables. There's also a notion of sparsity of statistical quantities, like in Peter Bickel's talk, that the covariance matrix was almost diagonal, had very few non-diagonal entries. Graphical models, Mike West's talk is another example. I'll pursue more this line that I'm going to assume that my data is low dimensional. And this appears in various different applications. And then, for example, you can assume that the data has an approximate, lies in an approximate k-dimensional space. So I wrote here orthonormal basis, but it doesn't have to be. It can be a concatenation of different bases. But I'm going to assume that it has an approximate, okay, maybe I should say sparse representation, but all signals have simultaneously a sparse representation. And I'll be interested in the effect of noise. So in this talk, I'll actually borrow sparsity from both words. I'm going to assume a linear function, and I'm going to assume that my data is low dimensional. But maybe slightly different than some of the other talks here, I'm going to assume that my predictor variables are corrupted by noise. So the model that I'm going to look at is a model where I look for a linear function, and I assume that my variables belong to a k-dimensional subspace, but they're also corrupted by additive noise. And the question that I'll try to analyze are, what are typical errors? What is the effect of noise in the predictor variables? As I've said, what are benefits of feature selection, of variable selection methods? And other thing that one might want to keep in mind is, how do we deal with unordered data? Data where we have huge number of dimensions, but each variable, there is no meaning to the order, like in gene expression data or stock data or document analysis data. Suppose you have such data. Suppose that you still have some approximate sparse representation in some unknown basis. How can you find such a basis? How much data do you need to find such a basis? So I'll here focus more on the first three issues, but these are also very important issues to think about. So as I've said, I'm going to assume a slightly different model from others, but I'm going to assume the following model. There is a response variable y. It's typically expensive, but for our purposes, let's assume that it's an accurate measurement. We know it without any error. And well, one option is to measure y, but it's expensive. On the other hand, we can measure x, relatively cheap, but noisy, high-dimensional measurement. A good example is exactly what Emmanuel said. Diabetes, instead of doing a blood punching and actually taking blood, just shine light, a different wavelength, hope for the best. I also tried that, not successful yet. Exactly. So for the data x, I'm going to assume, as I've said, that it lies in the linear subspace where the quantity of interest y is one of the factors. This is a linear factor model. And here I have k plus 1 components. So y is what the quantity of interest, and it has some spectral response v. But there are additional interfering components, and each of them has its own spectral response v. All of these are unknown to us. And in addition, everything is corrupted by noise. So this equation is, if you open almost any article in chemometrics or in spectroscopy, this is the standard model. It's also the standard model in many signal processing applications. So I think it's a good model to work, at least for some applications. So here's an example. This is data from Abraham Katzir's lab in Tel Aviv. And here they're trying to do the following. So blood and glucose is a very important problem, but also urine. And for example, the determination of citrate in urine, it's very important for people with kidney stones, like myself. It's very important to know what is the level of citrate. And so let's assume that Y is the level of citrate. Then measuring citrate chemically is an expensive procedure. On the other hand, shining light takes a millisecond. So here are typical things spectra that you get. Here are, let's say, 70 different samples. On these samples, they knew exactly the concentrations of urea, creatinine, citrate. And this is not urea. This is not real human urine. This was a controlled experiment where we mixed this into water. And in this example, we have 2,075 coordinates and only 70 samples. So as you see also, there is quite a bit of noise in this data. And as I've said, I'm going to look for a linear regression model. And ideally, I would want to find R and Y naught that minimize the mean squared error of prediction. And there are tons of different methods to do it: ordinary squares, classically squares, partially squares, principal component regression, ridge regression, support vector machines, etc., etc. In addition, some methods perform some pre-processing, like variable selection, feature extraction, normalization, pre-whitening. So there's a whole zoo of different methods that people apply. And I was interested in understanding how the mean squared error of prediction depends on the parameters: the dimensionality, the number of samples, the noise level. And as I've said, there are different ways to go about it. One is traditional statistics. You keep p and sigma fixed, and you do various asymptotics as n goes to infinity. Modern statistics, you let p to infinity, n to infinity, the ratio fixed. You should ask yourself, what does it mean to take p to infinity when you have these vectors v? You need to somehow explain. And do you keep the norm fixed, or let the norm increase, etc.? But as I've said, the approach that I'm going to take is keep p and n fixed, let the noise level go to 0, study how various quantities change with noise level. I'm going to average over noise realizations over the random vector xi, and I'll get various results, which I hope that they'll be interesting. And this method can be applied to other problems. Time permitting, I'll show analysis of principal component analysis and a rank determination algorithm. So, well, if we want to understand how the mean squared error behaves, and we want to know if it's big or large, we should first understand what is the optimal mean squared error possible. Because when a new sample comes in, it contains noise by itself. So there will be some uncertainty that we're not going to be able to overcome. And this is not difficult to prove. The optimal regression vector in spectroscopy, it's called the net analyte signal. It's the part of the response v of the vector v which belongs to y, which is orthogonal to all other interfering components. Okay, so I denote this by v orthogonal, and this is the so the optimal unbiased estimator has a regression vector which is proportional to this v orthogonal. So there's a very simple graphical interpretation. If this is the vector v that the response y multiplies, and here you have different other vectors of interfering components, the only part of v that you can use for prediction is the part that is orthogonal to all other components. And if the span of all other components includes v, in principle, you're not able to predict your response. So this is the optimal mean squared error that you can get. So now when we'll analyze what happens for finite p and n, we want to compute what we get to this optimal mean squared error. I just like to say that this is the optimal mean squared error for an unbiased estimator, and many of us know that you can do slightly better. You can do some Stein shrinkage, which slightly shrinks the estimator, and you can show that the shrinkage is, well, the shrinkage depends on the noise level, but it's relatively small, and you still get something like this, only slightly smaller. So I'm going to assume in any case that sigma, my noise level per coordinate, is relatively small, but I still have a huge number of coordinates. So let me first consider one of the simplest algorithms in chemometrics. It's called classical least squares. And this algorithm assumes that you know the number of components that you have in your mixture, and you actually even, in the training set, you even measured all of these components. So in the example I showed with citrate, creatinine, and urea in water, I really knew all of these 3 different components. And then you construct your sample covariance matrix of all, in my case, k plus 1 components. And you do 2 steps. The first step, you estimate the spectral responses of all components by simply doing this operation. So here you see the inverse of the sample covariance matrix. And, well, you design your experiment so that this will be invertible and well-conditioned. And the Vj hats are essentially the maximum likelihood estimates of the response vectors under normality. And then you compute the dot product of all of these responses. And to compute the regression vector for y, you need to do this operation. And then this is your prediction. So a question that one can ask is, what are expected errors of this procedure? And so first of all, it's good to know that if you do this procedure and the number of samples goes to infinity, then, well, this converges, let's say, to your population covariance matrix. If it's a random design, all of these quantities converge to their correct means. These are sample means right now. And you can show that asymptotically, you converge to the optimal unbiased estimator, which is a good thing. So if n is large enough, you'll be doing very well. But the question is, what happens for finite n? So as I've said, we'll keep p and n fixed. We'll actually even keep the realizations of all the random variables fixed. And we'll view noise as a small parameter, expand quantities in sigma, average over noise realizations, and get some average mean squared error of prediction. So first, a little bit of intuition. When is learning in this setting difficult? There are 2 different things that can make this learning difficult. One is if you have large correlations between different components, specifically a large correlation with the component y that you're interested in learning. Another option is that you have large interferences in the spectral responses. If the response vector of y is close to a linear combination of the others, again, you'll be screwed up. So 2 quantities come into play. One is the smallest eigenvalue of the sample covariance matrix. And the other one is the smallest eigenvalue of the matrix of all dot products of all responses. And intuitively, if these 2 quantities are small, you're going to have a more difficult calibration problem. And indeed, if you do the analysis, which is relatively simple, you see that the regression vector that you compute, so this is an expansion in sigma, not in 1 over n, contains terms which you see exactly 1 over lambda 0, 1 over mu 0, etc. And these are the psi1 and psi2 are averages of the noises in the n samples. And the key point to realize is that this one is linear in the training set noises with all entries order 1, but this term is quadratic in training set noises and has a mean of order p. So here you have a term which is p over n multiplied by various constants. And therefore, if you do a little bit of more calculations, you see that the average mean squared error of this procedure, okay, so this is the optimal part. If n went to infinity, everything else would be 0. There is a constant over n, which is where classical statistics would stop, typically. But this term contains sigma squared p squared over n squared. So if n is small, p is large, even if the noise per coordinate is not large, this term may dominate the overall error. So this shows you that even in one of the possibly simplest cases, you try to learn a linear function, your data is low dimensional, and in this case you even knew all the different components that generated that data. If you apply a simple algorithm, you might get very large errors. You could ask, okay, if you take the case k equals 1, then you can compute all the different quantities explicitly, and they all reduce to well-known formulas when you also take the dimensionality to be equal to 1. Now, what you could ask yourself is, well, that was for a specific algorithm that actually tried to estimate the response vectors of all components. Maybe different algorithms will have better performance. So I also looked at the partial least squares algorithm. It was mentioned here a few times. Partial least squares is de facto the standard algorithm in spectroscopy. And it's also used in economics, in bioinformatics, and in many other fields. And it has a very nice idea that you look for projections which are most correlated with your response. You look at the residual, and you redo it iteratively. So again, first of all, before analyzing what happens for finite n, we need to understand what this algorithm does, what is the optimal thing that it does. And you can prove, we have proved that in the setting that we described, if partially squares with at most k plus 1 iterations will converge to the optimal mean squared error estimation, to the biased one. So it converges to the, it does the optimal Stein shrinkage, so to speak. But again, using the same type of analysis, you can show that for finite n, the expected mean squared error looks like the asymptotic one. And again, you have the sigma squared p squared over n squared term. So again, both classical least squares and partial least squares may have very large errors. So by the way, so the conclusion so far is that standard linear regression methods, when you apply them to high-dimensional noisy data, give error terms of this form, which may dominate the overall error. And after we did this, obviously, you do something, and then you discover that many people have done or have reached similar conclusions in the past. So, for example, similar things also appear in classification methods. There's a paper by Donohoe and Buchheit, but actually there's a paper by Raudis in 1967 in Russian. I'd like to mention that support vector machines suffer a similar problem. It's not, they don't really solve the curse of dimensionality, so to speak. And what this also tells you is that maybe, maybe we should decrease this p. Maybe we should do some dimensional reduction, compression, variable selection, feature extraction. And then you could ask yourself, well, let's assume we do it. What is the benefit? What are we going to get out of it? So let me analyze a general low dimensionality mapping. I just take my data x and project it down into k different orthonormal projections. So for example, this encompasses all variable selection schemes, then the W's are just delta functions at the correct variables, but also any, I don't know, wavelet basis, Fourier basis, random orthonormal projections, whatever you wish is inside this. The nice thing if you do this is that because I assume the linear structure in my data, in the reduced space, I also have a linear mixture model. And the only difference is that now the noise is k-dimensional instead of p-dimensional. So all of the analysis I did before, keeping p and n fixed and taking sigma to 0 applies. And I'll just get the following formula. So P has been replaced by K. But now the norm of the net analyte signal, the part of the signal that was unique to Y, is replaced by T time, by its projection by T times V orthogonal. So this immediately tells you what you should be looking for. What is a good dimensionality reduction scheme? It's something that you represent your signals with as few features as possible. K is very, very small, much smaller than P. And yet you almost didn't lose on your net analyte signal. So in the language of the lecture by Cook yesterday, this is, I mean, a sufficient dimensionality reduction would be just to project onto V orthogonal. Well, if we knew V orthogonal, there would be no problem. The whole game was to try to estimate the regression vector. So perhaps we should use principal component analysis for dimensional reduction. Well, we know that it's mean squared error optimal in representing a given data. It finds the directions of the largest variance. So you could ask yourself, what are errors? So suppose you do PCA. You still have a finite data set corrupted by noise. And therefore, you can ask yourself, what are the errors in the projection computed by PCA? Well, if I state it slightly differently, how close are eigenvalues and eigenvectors of finite P and N covariance matrices? How close are these to those of the corresponding population matrix? Okay, and again, this has been a subject of a huge number of work. There is classical statistics, not starting, but a famous paper by Girshik, and there's a paper by Anderson, and the book by Anderson that describes it. There's been a lot of work on this joint limit, both in the statistics community, but also in the physics community. David Hoyle, I think, David Hoyle, I think, is here somewhere in the audience, and Peter Bickel also mentioned some of these people. And I tried to look if someone did anything with PNN fixed, and I found one paper by Pete Stewart, who's a well-known numerical analyst. So he had one paper in trying to analyze stuff with PNN fixed, but his bounds were very crude and global. So as I've said, we're going to do the same type of methodology. Keep PNN fixed, expand things in sigma, average, and see what comes out. Let me see if I want. Yeah, I won't go into all the details. I'll just show you an example for the case of a single component. What happens if you just have a single component corrupted by noise? There are various quantities that come into play. One is this quantity. Okay, S is the variance of the random variable that you have. This is essentially the signal part. This is interaction of signal and noise, and this is just a pure noise matrix. And you can write the covariance matrix, the sample covariance matrix, as a signal part, a signal-noise interaction part, and a noise part. And you can, again, we think about sigma as a small parameter, and here you can do various games. You can think about this as your base matrix, and this is your perturbation, or you can actually think about these two as your base matrix, and this is the perturbation, and you could do various stuff. Now, all of these matrices are obviously symmetric, and there's a lot of theory known about symmetric perturbations. For example, there's a whole book by Kato And one of the theorems says that if you have such a perturbation, all matrices symmetric, then all eigenvalues and eigenvectors of this matrix are analytic functions in epsilon for all epsilon on the real line. However, if you sort them in increasing or decreasing order, then when two eigenvalues cross each other, the eigenvectors may change abruptly, because at the crossover point you have a subspace of dimension 2 and things can rotate widely there. I won't go into all of the details, but you can just expand the leading eigenvalue and eigenvector of this matrix essentially in a Taylor expansion in sigma. You know that there is such an expansion up to a critical value, which is exactly where such a crossover will occur. And the key point that you get is that the average overlap between the sample, the VPCA is the vector of the sample covariance matrix, and the true one is 1 minus, and again you have this P over N term that makes your life hard. So if you do dimensional reduction by PCA, yes, it is mean squared error optimal in describing your noisy data, but not necessarily in describing the underlying noiseless data. And therefore, yes, here we now have only K instead of P, but we lost here an important term in terms of V orthogonal, and therefore, again, errors might be quite large. By the way, you should note that this analysis assumes that you used part of the training set to compute VPCA and another part to do the learning, because otherwise, if you do it all at once, there is the dependency between the noise in the projection and the noise used in the training data. So actually, the errors are larger if you use the training data twice. Now, what other things you can do with this matrix perturbation approach? So in the last few years, there's been a lot of interest in a phase transition. When can you even approximately learn the correct direction of a signal? And both Bayek and Silverstein and Paul, but actually, again, if you look at the literature, you find that people in the 80s in statistical physics found the phase transition that if P over N is small, you can approximately learn the correct direction, and if not, you can't. Here is a very two-line explanation of why this happens. So I need to use one result from random matrix theory, and that is that noise eigenvalues converge to 1 plus square root of P over N squared multiplied by noise level. And the other thing is that I use the analysis from the matrix perturbation that shows that the signal eigenvalue behaves like lambda naught plus sigma squared P over N plus order of sigma to the fourth. And I know from Cutter's theorem that when these two eigenvalues meet, then the eigenvector will totally change abruptly. So I only need to equate the noise and the signal eigenvalues, and I get up to a factor of a quarter, but I get an estimate of where the phase transition should occur and why it occurs. Once such a crossover occurs, the PCA vector just points in a random direction, which is 1 over square root of P, and if P is large, that is very close to 0. So here is a simple example. I had a covariance matrix with a single component, and here is sigma. So the blue line is the so-called the signal eigenvalue, and this is the largest noise eigenvalue. So as I start to increase sigma, this increases like sigma squared plus like lambda naught plus sigma squared. It's quadratic. And here exactly at I don't know, 1.8 more or less, the two eigenvalues cross, and here is the overlap. Here is this parabolic decrease in the overlap, but at this critical point, boom, you lose totally the relation between the largest eigenvector and the relation between the largest eigenvector and the correct direction of the signal. Okay, so to summarize so far, if we are in a high-dimensional setting, low sample size and noise, standard methods will fail. Doing dimensional reduction by PCA will also fail. How about variable selection schemes? So what is the performance of variable selection schemes? So variable selection schemes indeed decrease the dimensionality from P to K, but my claim is that unless your data is extremely simple, you will in general lose on the norm of the orthogonal. And now there is one misleading thing, is that if you're working in high dimensions, you may still get improved prediction errors when you compare to the full variable methods. Then you can publish a paper. We did variable selection and we got a 30% increased accuracy. So I want to show you a very simple example of that. Okay, so first, here is an example. This would be with one component. So the blue is the spectral response of Y. Later on, I'll have an interfering component V1, which here does not interfere with Y, but here in this region, it does interfere with Y. So the blue is the result of, this is a root mean squared error of prediction that I got for classical squares. For partial squares, this is dimension. And you see how, as I increase dimension, errors increase substantially. The green one is the theory. So you see that they more or less match. And for partial squares, they also match, unless for very large P, where there are things that I neglected. This is more, so this is for one component, and here is the result for two components. So for two components, this is how the net analyzed signal looks like. And you see that even though these two were very similar, there is still information in this part, in all of these variables, that can be used for prediction of Y. And this is how the optimal regression vector would look like. Now, to assess what the performance of a variable selection or a wavelength selection scheme, I took a standard method that was proposed by Spiegelman in '91. It's extremely similar to the method that was proposed by Ber and Tibshirani in '06, but this is what you get. So K here is your number of variables that you selected. So if you start from a single variable, the error is high. But as you add more variables, variables here are added according to their correlation with the response, the error decreases. And at about maybe 30 or 40 variables, you get an error of about 0.07, which is indeed lower than the error that you get for a full spectrum method. And indeed, maybe you should be very happy. I have a method that decreases my prediction error, and everything is okay. But for this example, noise level was 0.02, and the optimal error is actually somewhere around 0.04 something. So what I'm showing in red is the result of trying to do a dimensional reduction of this data into K different projections, in this case wavelet projections. Instead of trying to look for single variables, I try to find a subset of wavelet coefficients in which simultaneously all signals are represented well. And there is a methodology to do this that was proposed by Ronald Koifman and Wickerhauser, and also Naoki, Saito Naoki, and Weizmann. It's called joint-based basis. So here are the results that you get. You get far better results with far smaller number of variables. Now, one reason that we could do it here is that, well, spectroscopic signals are in general smooth, and therefore wavelets are a good basis in which all of these signals will be approximately sparse. So I'm going back to the example I showed on the urea, creatinine, and citrate in water. And here I took only a part of the spectrum, some 470 wavelengths. And here are examples of applying partially squares on the full spectrum, sorry, and on, or first projecting onto 20 wavelet coefficients and doing partially squares there. So the blue is on, so this is the x equals y line. So x is the measured value of citrate, and y is the predicted value. Everything, perfect prediction at all points would be on this line. And you see that working on the full spectrum in general has larger errors than working on the wavelet coefficients. And here the x-axis is the number of projections in partially squares, and the y-axis here is the root mean squared error. So you see that, for example, at 5 projections, we get much better performance working on only 20 coordinates, and also much smaller variance. These are results over many simulations taking different random training and test sets. So we get better prediction errors and smaller variability. Now, I think one challenge if you want to deal with modern data, specifically with unordered data, is well, their wavelets are not the correct basis. And one question is, so assume that you're given unordered data where you have a huge number of variables, no meaningful order to the actual variables. If you do assume that they're low-dimensional structures, how can we find them? How much data is needed to find them? I'm not going to talk about it today, but we have some preliminary analysis of some of these questions, at least for very simple settings. And Anli, my collaborator, will talk about it tomorrow, hopefully. In the last 5 minutes, I'd like to show you another application of this idea of small noise expansions to a problem of rank determination. So the previous work was work I did with Ronald Koifman, with Anli, and with Larry Wasserman. And what I want to present right now is joint work with my student, Shira Krichman. So I'm going to, again, consider the factor model with k components, additive noise, and the problem is as follows. I give you observations from this model, and very simple problem. Infer what is k. What is the number of components? And this is a fundamental problem in spectroscopy, in signal processing, in blind source separation, tracking, detection of arrival. Before you want to know how many planes to track, before you start tracking planes, you want to know how many planes to track, or etc. And there have been, I counted 30, but I guess there are more than 30 different algorithms in the literature, and maybe there are other approaches, but essentially there are 2 different approaches that I can think of. One is doing a sequence of nested hypothesis tests, and this goes back to Bartlett and Lawley. And at least in chemometrics, there are 20 different algorithms that do one or another modification of this approach. And complementary, there are model selection methods. There's a famous paper by Wax and Kailath, a similar paper in statistics, and many other papers that along these ideas. And the challenge is obviously, so you get your data. Let's say you compute your sample covariance matrix, and here are the eigenvalues. So hopefully here there are 1, 2, 3, and 4. This is n over p is 4, so this is a large sample size. So here it's relatively easy to find that there are 4, but when sample size is 64, dimension is 256, now it's less clear, and specifically, is this eigenvalue signal or noise? So you want to be able to distinguish between insignificant yet large noise eigenvalues and significant yet small signal eigenvalues. And now, again, I'm going to use results from random matrix theory, specifically a result by Johnston that the distribution of the largest noise eigenvalue in this joint limit converges to a Tracy-Whedon distribution, and there is a nice paper by El Karoui that does small modifications to these quantities to get second-order convergence. So if my noise level were known, I could just test which eigenvalues are larger than this quantity, pick an S appropriated for some confidence level alpha, and I would be done. But, well, I also have to estimate somehow the noise level, and the idea we took here, I'm not going to show the details, but you need to somehow understand the interactions between signal eigenvalues and noise eigenvalues, but for finite p and n, because this is the data that you have. And this gives you a method to estimate noise and therefore to use that methodology. And here are just a few examples. So, so the green one is the performance of our method. The y-axis is our probability of correct rank estimation. The x-axis is the dimension. And in these simulations, we took 4 components with a very large range of signal strengths. Noise level here is 1, but we don't know it. We try to estimate it. On the left, it's a more difficult problem. The ratio n over p is 1/4. On the right, it's 1. So here, for example, for low dimension, so if n is 64, if p is 64, n is 16, very small number of samples, our success probability is less than 40%. It gets close to 1 in higher dimensions and also increased sample size. And the other curves are other algorithms. For example, this one is an algorithm by Faber and Kowalski in chemometrics that was proposed. The purple one is a recent algorithm by Rao and Edelman from MIT, recently proposed to exactly consider this setting. And if n over p is 1, have many, many more samples, our algorithm, its performance is very close to 1, and other algorithms perform typically worse. And we have many, many other simulations that can also prove consistency of our algorithm, etc., and other various different scenarios. So in summary, I presented a somewhat different approach to think about learning problems. I keep p and n fixed. I look at the effect of noise by expanding things in noise level, similar to the lecture we had yesterday by Fan. There is an issue of accumulation of noise. If you have a huge number of dimensions, noise is accumulated, and somehow you need to understand how to do good dimensional reduction prior to learning. So indeed, the challenge, as we've seen in many talks today, is how do you do robust feature extraction given data, or efficient or robust sufficient dimensionality reduction. Global methods such as PCA, if you have noisy data, low sample size, are generally may not be optimal. There are various papers on my website. Thank you.
Questions?
We see more drag out papers from the 1918 geophysics. But have you ever come across some papers by Park and Che in the 1980s, where I think they also fix P and N and do an expansion in terms of sigma?
No, I'm not aware of that. I'll be glad to get the reference.
Yeah.
Other questions? It's late. Oh, thanks.
I'm just wondering how much of this noise analysis is kind of dependent on specifically this kind of factor model?
Well, the benefit of having a very detailed model for my data is that I could, first I knew what the answer would be, and therefore I could compare what I'm computing to what the answer is, and therefore get errors, etc. So, I don't know.
It's
I mean, to do this, to some extent, you need to specify some type of model for your data to do the analysis.
You know, I don't know exactly the connection, but you know these recent papers by Len Stefanski? He's actually, rather than expanding, he's done small noise stuff where he does measurement error. He's actually adding noise in simulations and watches where the noise goes. And rather than having to use analytic expansions, you might look at it.
No, I'm not aware of that, but there have been works on actually taking a data, adding noise, and see how the regression coefficients change in order to try to assess which are robust and which just float around.
Other questions? Well, since we've been doing references, actually, I guess, Doxam and I long ago, and I think Chernoff before us, also did expansions in terms of small sigma in situations where when sigma equals 0, things are well defined, but as soon as you move away, then it's not quite clear what you're doing. A paper that we had that are called Great Trouble with David Cox on analysis of transformations, revisited. Anyway, thanks again. Is everyone present with